Check this out. We've got something really fun today. This is so amazing. Oh man, again? 11.3, integration by substitution. If we have composite functions, we would have used the chain rule to find the derivative. It can be difficult to see what the antiderivative would be if we're trying to integrate, so we can simplify problems like this by substituting the inside function with a single variable. And you'll probably see the derivative of that inside function elsewhere in the integrand. Substitution is a tool we use to simplify integration and is not necessary. But if the question is unfamiliar or the derivative of the inside function somehow cancels out another part, it can be extremely difficult to find the antiderivative without substituting. Let's take this really easy example here. We want to find the indefinite integral of x squared minus 5 to the power of 8 times 2x. And you can see that this inside function here, if we took the derivative of x squared minus 5, we would get the 2x. So I can figure out the antiderivative of this. This probably was 9 before, and I don't see a 9 here. So I'll put a 9 in the denominator to cancel out that 9 that I know is coming down from the exponent. We take the derivative of the inside and that would give me 2x, and that's exactly where this came from. And since it's an indefinite integral, I'll need a plus c. Now this question is extremely easy, and so you can see we did it without substituting. What we want to do with substitution is take the inside function, we'll call that g of x here, and we're going to replace it with u. And u is so commonly used that this is often called u-substitution. You see that g of x is inside some function f of x, and then there's the derivative of g of x here. In our case, we will let u equal x squared minus 5. We'll take the derivative of both sides of this equation, and on this side we'll just get a du, and on this side here we'll get a 2x dx. Now we can make the substitution, so we'll have our integral sign, then we'll have this just equals u to the power of 8, and the 2x dx is just replaced with a du. And now you can see we're doing an integral with respect to u. And this is really easy, much easier than the mental math that we needed to do here. So this would just be u to the power of 9 over 9 plus c, because it's an indefinite integral. And then we can sub out our u again and put the x squared minus 5 back in the numerator there. And you see we got the same answer, but this was a lot easier. Here's another example where we can see the inside function here is a cubic. It's inside a radical. And if we take the derivative of this cubic, we're going to get this x squared term. So this will definitely be our u that we want to substitute. So u equals 1 minus x cubed. Now we'll take the derivative of both sides, so we get du is equal to negative 3x squared dx. Now we want to substitute all the x's out, make sure that they're all gone. So we have the integral here, and we've got a 1 over the square root of u. And we have an x squared dx left, and that's not what we see in this equation that we made. So we just need to do a little bit of algebra to make an x squared dx. So we'll divide both sides here by negative 3, and now we see that x squared dx is equal to du over negative 3, or negative 1/3 du. Now, this is just a constant, and whenever you have a constant, it's probably best, unless it's going to do something important in here, it's probably best to put it in the front and just let it stay there. So we'll say negative 1/3, and the integral of 1 over root u du. And you can see that our integral here is in terms of u, and there's no more x's here. So we have our negative 1/3. The antiderivative of 1 over root u is root u, and if we had root u and we took the derivative, we would get a 1 over 2, and I don't see that, so I'll put a 2 here in front to cancel that out. And it's an indefinite integral, so I'll need a plus c. And I'll just tidy this up here. How about negative 2 over 3 and the square root of u, which was 1 minus x cubed plus c. Now, if there's not one function obviously inside another function, it may be difficult to decide what you should make u. So do some mental math, and if you take the derivative of the natural log of x, you get 1 over x, and so that would explain 1 over x's presence here. If you make u 1 over x and try to take the derivative, you will not get the natural log of x. So we will make u the natural log of x, so that when we take the derivative, we get 1 over x dx. Now we can make the substitution. This is just u, and the 1 over x dx is just du. So this couldn't be easier. It's just u squared over 2 plus c, and we'll put our x back in here. Natural log of x squared over 2 plus c. Now we have to be careful when we're doing definite integrals and we use substitution. So let's let u be e to the power of root x, and that's because when we take the derivative, we get this other term here. So e to the power of root x times the derivative of this, which is 1 over 2 root x, and there's a dx at the end of this. And now we can make our substitution, and we see that this equation right here has almost everything we need, except it's got this extra 2 here. So let's do some algebra. Put the 2 over here, so it's 2 du is equal to e to the power of root x over root x dx, and that's actually everything we need right there. So we can say 2 du in our integrand here. Now these values, these upper and lower bounds, were x values, and we're not integrating over x anymore. So we need to change those limits of integration. So we'll say if x is equal to 1, taking the lower limit here, then we just plug it into this equation right here and get the corresponding u value. And we'd have u is equal to e to the square root of 1, which is just 1. So it just equals e. So our new lower bound here would be u equals e. And if x equals the upper bound of 9, then we'd have u is equal to e root 9, and that would give me u is equal to e cubed. So that's my new upper bound. And now I can do this definite integral. So the antiderivative of 2 is 2u, and we need to evaluate it at e to e cubed. So that will be e cubed minus e. And if you like, you can factor out. This is mathematically fine. You can factor out an e though, since we already factored out a 2. At least I did. You can factor this as a difference of perfect squares, but this looks fine. It really depends on what you're going to do next with this that will determine what form you want to leave it in. Now let's try this question, but without substitution, just to show you how it would work. Okay, so our integral was from 1 to 9 e to the root x over x, root x dx. And we take the antiderivative of this, and we can see that that would have been e to the root x, and we take the derivative of this, would have given us this, and a 1/2, which we don't have, so that will make a 2 show up right here. And then our limits are 1 to 9, and we can put them in. So 2 e to the root 9 minus 2 e to the root 1, and this gives me 2e cubed minus 2e, which is exactly the same as what I got above. You can see that we get the equivalent answer. It's just that this antiderivative step right here was a lot more difficult. Find the area under the curve y equals 1 over 2x plus 1 from 0 to 1. Okay, so we've got our area. We're going to integrate from 0 to 1 the function here. Now this looks interesting, and we can use our u-substitution. So we'll let u be, how about the whole denominator here, that linear function. And that way our du is equal to 2 dx. And I don't see a 2 here, so I'm just going to rearrange this. Divide both sides by 2. And now we can do our substitution. So this is just 1 over u, and this is du over 2. Now we're in terms of u, and these old limits here were in terms of x. So we need to change those. So we would have when x is equal to 0, then u equals 1. Let's put in that equation there. And we'd also have when x equals 1, then we'd have u is equal to 2 plus 1, which would be 3. So there's our new limits of integration. We're going from 1 to 3. This time it's u equals 1 and u equals 3. Before it was x equals 0 and x equals 1. Now this looks a little bit awkward here, so this is a constant. So remember, bring it to the front. That's the easiest place to leave it. So we have 1 over 2. Now we'll take the antiderivative of 1 over u, and that would be the natural log of u. We want to evaluate this from 1 to 3. 1/2 is our constant. We'll leave it out. The natural log of 3 minus the natural log of 1. And the natural log of 1 is 0. And so we can simplify this to 1/2 the natural log of 3. Now, some students do not like to find the new limits of integration. So they want to, at this step here, after they've used the substitution and found the antiderivative, they want to put the x equation back in. So that eliminates u, and then they can use the original limits of integration. Now the problem with this is that in this step and this step, if you wrote 1 and 0, you'd be mathematically wrong because this is in terms of u. So unless you're going to do some sort of side work here and show an indefinite integral separately, you need to change the limits of integration. You should be able to integrate using substitution. There's some questions from the textbook. Give them a try, see if you know what you're doing.